right. Example 11, we get started. A 75-kilogram astronaut exploring the surface of a rogue planet that has entered our solar system. Before landing on the planet, he measured the diameter of the planet to be 638 kilometers. He drops an accelerometer, and it records the acceleration of 3.6 meters per second squared. That's on the surface. What is the mass of the rogue planet? What is the force of gravity exerted on the astronaut? So, I've drawn a little picture. And here's our little picture. Now, it says the rogue planet has a diameter of 638 kilometers, right?
Yeah.
So, that's across what? Across the whole planet, right? So, this right here is 638. Good, we got to cut it in half to get 319 kilometers. Now, this is not the scale, otherwise that is a very tall astronaut. All right. So, 319 kilometers.
We gotta make that meter.
Got to make that meter. So, the radius is 319 kilometers. Now, remember, kilo means times 10 to the third, right?
Yes.
319,000.
So, 319,000 or 319 times 10 to the third meters. Could also write it as 3.19 times 10 to the fifth. Okay. So that is our radius. Does that make sense, guys? Yeah, are there any question about that? No? What else do we know? We know the mass of the astronaut is what?
75.
75 kilograms. Okay, what else do we know?
The
Acceleration due to gravity?
yeah.
So little a or little g, Reggie, pay attention. Okay. What is that?
3.6.
3.6 meters per second squared. Kyle, Rex, you guys got issues?
Wait, what? Why?
Why are you throwing me in stuff?
Because you're talking to him.
Wait,
I wasn't talking to her.
Okay, you're talking. All right. Any questions? Anything else to add? Is there any other variable we know? Or constant we know?
G.
G, what's big G?
6.67.
Times 10 to the negative 11.
It's newtons meters squared per kilogram squared. Okay. And so the meters and the kilograms cancel out, you left with newtons. All right. All right, any questions?
You just
No.
put newtons.
No questions?
No.
Well, then nothing would cancel out when you use the equation. So that's what we know. Now, what are we trying to find? That's Earth for later. What are we trying to find?
Big
The planet's mass. So we want to try to find big M.
Yeah.
So where do we start?
equations.
L.
Okay. So somebody said equation 6. Now the M in equation 6, which M is that?
It's big M.
Big M. Big M.
Okay, we got a little converse opinions here, right? Is it little m or is it big M?
Big M.
Big M.
Okay, good. We learned last week that that is big M, not little m. If you plugged in 75 for M right there, then you are doing this incorrectly. You're finding the acceleration of the gravity on the surface of the astronaut then, not the planet. Okay? Remember last week we learned the only thing that affects acceleration of gravity are what two things? The radius and the mass. The mass of what?
The big
Which is the mass of what?
thing.
The thing. What am I on right now? Earth. Well, Earth is a type of,
Sphere.
looking for a word that means wanderer.
Planet.
Planet, thank you. Okay? Gosh, we need to be like on Pictionary together or something. All right. So, yeah, planet means wanderer. Planetes, Greek word for wanderer. Because planets were wandering stars. They're going to stay in the same spot.
That's so cool.
No.
I didn't know that.
The Greek astronomers would look up at the sky and they'd see the stars, and then they'd see stars that weren't in the same spot, even as the night went on, and they called them wandering stars or planetes. And that's where we got the name planets from. Because they make loops in the sky, they don't go straight like the stars do. Alright. So, little foyer into Greek there. Alright. So this M right here, that is the mass of the planet, right? The big object.
Yeah.
Right? So what Galileo, we learned this last week, what Galileo said, when you drop two objects of different masses, they hit the ground at the same time. So the mass of the objects didn't affect the acceleration due to gravity, right? This equation confirms that because that M is the planet mass. The only things that affect acceleration due to gravity is how far you are from the center of the planet and the mass of the planet. Nothing else affects it. All right? Not even the mass of the object you're dropping. Okay. Now, if we start thinking about friction and air resistance, then cross-sectional areas get involved. But we're going to leave that out for now. So acceleration equals G, big M over R squared. So we want to find big M so we can start plugging things in. What's A? 3.6. Big G, 6.67 times 10 to the negative 11. We don't know M. And R. Now R gets some controversy here. I bet somebody plugged in 638 because that was the diameter. Right? Did anybody plug in 638? Okay. I bet someone just plugged in 319 because it's in kilometers, right? We thought that was right. We need to work in what? Meters, which is why it's 3.19 times 10 to the 5th. So 3.19 times 10 to the 5th squared. We're doing algebra, so I like to do 6.67 times 10 to the negative 11th divided by 3.19 times 10 to the 5th. If you did not, that's fine. You can do it without doing this. Oops, that's log, not squared. So, Rex, we got 6.55 times 10 to the negative 22nd. Big M. What do we do now? Divide. No, this is algebra.
But algebra is hard physics.
Algebra is a tool for physics. It's like Batman. It's like Batman in his grappling hook, or his gun thing that shoots the. You know what I'm talking about. Okay. Well, it's not Batman. It's his tool. All right. So 3.6 divided by 6.55 times 10 to the negative 22nd. What do we get? So 5 point what? 49 times 10 to the 21st kilograms. So, is the rogue planet bigger than the Earth? Not in my drawings, but is the rogue planet bigger than the Earth? No. It's actually 1,000th of the Earth.
You sound weird. I got the right answer.
Are there any questions on how we got that mass? No questions. No questions? Okay. So that's the mass of the rogue planet. What was the next part of the question? We need to find what?
I got that into two.
We need to find the force of gravity of the astronaut. Good. We need to find the force of gravity of the astronaut. I'm going to erase the Earth. Hopefully it doesn't hurt anybody. All right. So we're going to find the force of gravity of the astronaut. So which equation do we use now? 5. So F equals G-M over R squared. Now the nice thing here is the radius is the same because the astronaut's on the surface. G is still the same, 6.67 times 10 to the negative 11th. Big M we just found, right? And little m is 75. So we end up with this 6.67 times 10 to the negative 11th times 5.49 times 10 to the 21st times 75 all over 3.19 times 10 to the 5th squared. And we can find our force of gravity exerted on the astronauts. 270.
Can you just do math on acceleration?
Can we just do math times acceleration? Well, what do you think?
Yes.
What acceleration are you going to use?
3.6.
Okay. So Nan is suggesting we just do 75 times 3.6.
That's an astronaut.
Does that work? Okay. If we look at this equation, this right here, gm over r squared, isn't that acceleration? So this right here is really g, isn't it? Right? Remember force due to gravity, F equals mg. Right? Where g is acceleration due to gravity. This is g, which we learned earlier was 3.6, right? So yes, we can really just do 3.6 times Nope. We can really just do 75 times 3.6. Because 3.6 are those three things arranged in that order.
Wouldn't the 75 have to be divided by the radius too?
Nope. Because multiplication and division are on the same part of the order of operations, Skylar. So if I divide these by the r squared, then multiply the mass, that's fine. If that wasn't the case, then F equals mg, which we used previous this year, would have been wrong the whole time. Okay, but it wasn't wrong. So if you do that, you get the same thing, 270.
Why did you do this?
All right. Any questions? Any questions?